All right, now everyone's muted. So, all right, welcome to the first completely virtual stochastic empirical loading and dilution model class. This presentation is the class introduction. We should be able to get through it fairly quickly. All right, just as an overview, SELDM was tested and reviewed by 43 professionals from USGS, EPA, Fish and Wildlife Service, 16 state agencies, 15 were people in the state DOTs, some of which were on this call, and there was one Massachusetts state regulator, the Massachusetts Department of Environmental Protection. Other people were also invited. These are the people that stepped up to the plate, help us design, beta test, and review the model. SELDM was developed by the USGS in cooperation with the Federal Highway because we kind of have an overlapping mission. We provide science to other federal agencies and state agencies, unbiased science to help them make decisions. So as part of our role, we work with Federal Highway to develop this model. We worked with EPA and other folks to make sure that the model would be acceptable to them for decision-making purposes. So SELDM was designed as a highway model, but it could be used for other developed land covers. So we recently had a journal article come out where I worked with a professor from Roger Williams. We looked at urban inputs and how that compared to these total impervious area thresholds for adverse ecological effects. So this little slide shows on the left kind of the SELDM, which is what's called a lump parameter model, where you have this upstream watershed and you have a stream that comes to a point, and at that point you would have your highway. And at that highway, you look at your mass balance, where you have your upstream loads, which are concentrations and flows, your runoff loads, which are concentrations and flows, and then your downstream loads and flows, which are the sum of the components, and then your downstream concentration is the load divided by the downstream storm flow. So the traditional application is where you have perhaps a highway, or that highway could represent like a collection of the highways upstream in the basin, kind of that total area, and then some representative hydrologic characteristics. We can also, using this method, model like urban areas. So the one on the right is, if you can imagine those two white cutouts were the places that the urban areas physically are, but we kind of accumulate that urban area down at the basin and kind of see what the cumulative effect of all the different urban areas might be using the same mass balance approach. So SELDM's like a really simple model. It's easy to learn, very easy to use, because we've preloaded it with statistics. You can be up and modeling and get results within an hour or two versus some of the complex watershed models, it could take weeks to months to calibrate to get, fairly decent answers. Initially, Federal Highway worked with the USGS to develop SELDM because to replace the old Federal Highway runoff model, which was for the National Environmental Policy Act process. So that was, this sort of proposed action, you're going to do something. There's this coordination and analysis, and then you come down to the $1 million question, is there a significant impact? So with SELDM, you can often show fairly quickly that yes or no, there's a substantial risk for an analysis. For example, out in Illinois, there was a bridge that they were expanding over a 3,000 square mile watershed. Fish and Wildlife Service was worried about mussels there. Common sense would say one bridge, 3,000 square miles, the bridge probably isn't going to make a difference. But the DOTs out there were able to use SELDM to show that, the bridge's additional impact would be pretty infinitesimal. So there can be these very quick yes or no, is there a problem? If it's unknown, you can come back and you can rerun SELDM, or if there is a problem, then you can add in BMPs and say, well, will there still be a significant impact? So you kind of add a BMP into SELDM and see what it is. Andy from North Carolina is on the call today. they have a project right now where they're running SELDM a bunch of times to come up with like a very simple decision tool. So they're doing a ton of runs so that, their highway folks don't have to learn how to use SELDM. So it's kind of putting us out of business. I say that jokingly, but it's better for the DOT because they can kind of make instant decisions. And if they're in a place where the risk is higher, or if it's a sensitive like ecological problem, then of course they can go back for those specific conditions and run the model. SELDM is also used for TMDLs. These results are for total phosphorus in Oregon. In that, we did a study of the Willamette Basin, and using that lump parameter concept, we looked at agriculture, developed areas, state highways, undeveloped forest. Although the highways, because they're 100% impervious, and they had higher concentrations than these other land covers, had higher yields because the state highway areas were very small. The state highway system was a very teeny amount of the load. And in that study, we showed that, even if you took out all the state highways out of the whole Willamette Basin, you'd only reduce the loads by 2.5% versus if the agricultural guys could just do a teeny bit better because they're such a big part of the pie, then, they could have a much higher impact. So that's kind of the decision-making information that SELDM can provide. Right now, SELDM has been presented in 10 classes and being used in 13 states that we know about. This map shows the physical SELDM class locations. I don't know how I'm going to put this year's class on the map for next year's class, but so the SELDM classes in the past are in blue. The states using SELDM on their own are light green. That's Washington State DOT. A number of states are using SELDM in conjunction with USGS studies, and then there are several states using SELDM with universities or the private sector. And there may be many more states where SELDM's being used. It's just the people haven't contacted me, so I don't quite know about it. Also, the National Cooperative Highway Research Program put out a report, I believe it was the end of last year, the approaches for determining and complying with total maximum daily load requirements. And in that, they kind of recommended SELDM as the method to come up with the yields and loads for highway areas. All right, so that's kind of what SELDM can do for you in a thumbnail. So as I mentioned, this online class we're kind of in beta test, trying to figure out how to do it. So what we're looking at is what's known as blended learning. So we'll have a combination of, well, we won't have a physical classroom, but this will be kind of the surrogate for a physical classroom where we might have periodic webinar meetings. And the main way we're going to communicate the theory to you, so we don't have to have you sit here and listen to me for a bunch of presentations, is that we've recorded a bunch of YouTube videos. We'll provide the links. And we have the SELDM Web Page that has all the documentation. It has USGS reports and TRB articles and journal articles that show example applications of SELDM, which can be informative. Class materials, typically I hand out a DVD to everyone in the class. We'll have to figure out among ourselves how to get you those class materials. I think I'll put the files on maybe an FTP site. The whole CD has a bunch of files, reports, software, etc. So it might be a big download. We can talk, maybe people can try the FTP, and we can talk perhaps, I've obtained a bunch of thumb drives, and I might be able to FedEx people who have trouble with the downloads, a thumb drive with all the files on it. But for that, we need to send it to, a location that you can access. I don't know. I need special permission to go to the office, so you know, to be able to go get it, you know, we might have to figure out the best place to ship a thumb drive to you. So question here, small groups or teams, if people really want to become modelers, you know, I guess you guys could, we could either organize formally or informally people who might want to work together. Typically when we run SELDM in the classroom, it's good to have a couple people work together, kind of one person listens, one person types. So people tend to be able to answer each other's questions and make it work smoothly. I guess if we're all stuck in our own little spheres someplace, then, you know, that might be more difficult. Homework, question mark. Some of the YouTube videos show kind of class exercises. Some of it's playing with online USGS applications. I guess we could talk about, you know, whether we want to do formal like assignments and then talk about them later. And when I say assignments, we'll put that in quotes. You know, it wouldn't be something that anyone attending the class would have to do. It would be kind of what you want to do. And, you know, this final bullet, I'm open to suggestions. Like I said, this is a beta test class, trying to figure out how to do it. I guess I'm suffering as many teachers and parents are through this, you know, this new teaching method. So I'm very much open to suggestions and, you know, 4 different groups. If you want to just casually kind of get an overview of what SELDM is and how it's used and how it works, or, you know, like I said, if you want to really dig into it and become a SELDM modeler. I like to say one of my dad jokes is that, you know, SELDM is kind of like online shopping. If you can online shop, you can run the SELDM interface. It's just a series of forms where you put stuff into text boxes and you push some buttons, but it never asks you for your credit card. So in that way, it's better than online shopping. But I guess the downside is you don't get something from FedEx, you know, on your doorstep. So I guess it could be worse than online shopping. Typically, we do, like I said, in-person 3-day remote classes. So it's like being, you know, in the shining city on a hill. When you're away from your job for 3 days, you can focus on that one thing for 3 days. Your boss isn't expecting you to do other things. You don't have other demands. So this online, we'll try to schedule multiple sessions so we can fit in within people's time frames, but hopefully, you know, you're not flying away to go to a class, but hopefully we can carve out some times that are, you know, mutually agreeable. Also, going to the online class is more fun. There's more synergy to get a group together. Well, no, not the online, but the in-person class. There's more synergy to get a group together, and you know, people get to know each other. So we'll miss out on that. I guess we could have some free-form discussions. Again, for that, I'm open to suggestions for that. And as I mentioned, YouTube will be the primary platform for asynchronous learning, so that we wouldn't, you know, the in-person classroom class is basically 3 days, 24 hours. We wouldn't want to be spending 24 hours on web meetings. I think our ears would hurt from the microphones, or not the microphones, but the headsets. So YouTube will be the primary platform for asynchronous learning. There's about 2.36 hours of quote unquote mandatory lessons. So that would be like if you were in the, it's a little bit more than if you were in the class, but that's kind of the theory. The 2.36 hours is kind of overviews of each part of SELDM. The 2.63 hours are recommended parts. So that's like for water quality, there's kind of an overview presentation, and that would be the quote unquote mandatory session. Then there's more of a deep dive on different aspects of water quality, and those would be the recommended. And then there's like about an hour of further recommended content, and you know, that's completely optional, and it may be of interest to you, but you know, it may be trivial to you. For example, There's a video on how to delineate a watershed. So that might be, you know, that may be way too basic for you to spend your time on. Now, when I'm saying 2.36 hours, don't get scared. There's not a 2.36 hour video. They're all like 5 to 15 minutes at a time. So you can take them in small bite-sized chunks. And if we're meeting every other week or every couple of weeks, then you can take your time getting to different things. They are individual videos, but they're also grouped in playlists. And I guess I should state at this point, if you guys need professional development hours, please keep track of what you've done in class and what you've done outside class, and kind of towards the end of what we're doing together, we can I can put together some like PDF certificates that you could put in your file. If I think different, what is it, about 16 to 20 hours, depending on your state, that you're supposed to get every year or every other year. So you can use this SELDM class for professional development hours. That being said, we haven't like registered with any state boards, but I think in the past, usually most states allow you to self-report as long as you have some proof you've received training. So when you go to the YouTube page and you look, each video has an explanation down below. And then there's a little show more that I barely ever noticed, but if you click the show more, then you get more information. I think you can even see this before you actually start playing the video, but it gives you more information about what that video is about, and then it has like references and links to the sources of information. So if you want to dive even deeper than what you see in one of the YouTube videos, you can, go to that underlying information. I guess for the YouTube, the channel is not monetized, so no one's making any money from this channel, and I hope that you don't have to see any commercials. I don't know if YouTube does that on their own. When I've looked, I haven't had to, click through any ads. But hopefully as you do it, and especially if you're going to do professional development hours, if we work together, or if you will do a few things, it will help other people find the SELDM videos and help spread information about the model to others. So the way the YouTube algorithm works is, how many clicks, how many times people click on it. If they watch it, do you watch it through, or do you click in and out? So I guess I'd appreciate if you click on one and it starts to play, you just let it play through to the end. You can mute it and put it in the background, so if you accidentally click. And this engagement, it'd be great if you guys could do, and now I sound like a YouTuber, but if you can like and subscribe, that would help other people find the content. And I know I don't think I can do either with my work email, but typically you can just set up kind of a fake Gmail account, or a dummy Gmail account, and do it there. One good thing, people don't have a commute anymore, but if you do have a train commute, don't be doing it while you're driving. But these videos I tried to size the graphics so they'd look okay on a smartphone. So in theory, you can watch them on a smartphone if you have a train commute. Let's see, there's also the SELDM Web Page. On that page, I mentioned there's all the information, all the previous reports. There's links to software, the highway runoff database. There's a bunch of case studies, the manual, all kinds of stuff. And we keep updating this as we publish stuff. So this is kind of a living page. Hopefully I haven't scared anyone. With this class, there's different people with different needs. So you get to decide, I guess if you go to the 3-day class, you're kind of stuck at the 3-day class. We try to have them in nice places, but with the virtual class, you can decide how involved you want to be. You can get a general feel by watching the videos, or, you know, if you want to get more active and spend time playing with the model, it's pretty easy to become a fairly expert SELDM modeler. And over the years, we've developed tools to help with the inputs and the outputs. All right, let's see, page up. I'll leave that slide on, and now I'll unmute everybody. Does anyone have any questions at the end of you know, that introduction?
Hey, Greg, this is Bhaskar.
Hey, how are you?
Good, how are you doing? You know, you mentioned that report, the NCHRP report. So you said SELDM is the only model recommended there, or are there others or other methods, or what? Or is it like, are the, yeah.
I think that they mention other models, but they mention other models, but SELDM is the primary model that they use because it is easy. It is fairly easy to use and easy to come up with yields for different land uses, including highways.
Yeah. Yeah, because the title of the report says TMDL compliance, and I was thinking earlier you said this is a planning level tool, so can it be still used for compliance demonstration? Is that what that report is saying?
That's what they concluded. You can, I guess I would suggest, you know, maybe go look at it. You can, but yes, I think they.
Okay.
Basically, the idea is that you use SELDM to come up with yields, and you perhaps, and I know Mass Highway has done this out on Cape Cod, I believe, but you know, you come up with a yield using SELDM, and then they use GIS to apply those yields to the amount of area that they own in a given watershed.
Okay. Okay, thank you.
All right, let's see. So now I guess I will switch over and do the, I'll do kind of the more formal introduction to SELDM. And kind of go through this, and then we can talk about any further questions once we go through this. So I'll just mute folks so we don't get too much background information. All right, so this is the Stochastic Empirical Loading and Dilution Model class overview. It's kind of give you a general idea of what SELDM is and how it works and what's in it for you. Let's see. Whoop. Actually, this is the wrong one. And I guess it's this one, right? Okay, so SELDM provides concentrations, flows, and loads of stormwater. SELDM is the stochastic empirical loading and dilution model. It's stochastic because it uses Monte Carlo methods to create a sample of events representing the combinations of flows, loads, and concentrations that would occur over a number of years. It's empirical because it's based on data and statistics rather than pure theory. For example, for BMP treatment, we're not trying to run Stokes' law when you really look at how temperatures and grain sizes and densities of sediment in BMPs varies. You know, you really can't characterize what's going on. So instead, what we did was we used data from the International BMP database to say, compare inputs and outputs from BMPs to get these statistical transfer functions. The good news is it's based on statistics, but between the highway runoff database, the BMP studies we've done, and the hydrologic studies we've done, we've calculated all the statistics for you pretty much. You need to just put in some site-specific characteristics and maybe pick some water quality data that's relevant to your area and then proceed with that. SELDM's a loading model because it provides storm and annual loads, and it's a dilution model because it does the mixing of the upstream and the highway, or highway, quote unquote, or maybe urban, to indicate the chance of exceeding a target value with and without BMP treatment. So this is just kind of a schematic diagram of a river with a highway going across it. We see we have an upstream load. We have a concentration, upstream concentration, and upstream storm flow. We have a highway or urban runoff load. We have a concentration and a storm flow. So all these variables are created by using these stochastic processes. So these variables are all random and vary from event to event. Now the highway/runoff load can also be modified by using BMPs in the same run. So you add the upstream load to the highway runoff or BMP discharge load, you get the downstream load. You add the storm flow from upstream to the highway or BMP discharge storm flow, you get the downstream storm flow. You divide the downstream load by the downstream storm flow for each event, and you get that downstream concentration. So you get these populations of concentrations and flows for all these events. So you can kind of gauge the risk of what's the risk of something, an adverse effect from runoff. So here's a schematic diagram that kind of shows the hydrology of SELDM. We have this rectangle up on the top are the storm event statistics. So we're randomly generating all these storms. The same storm is applied to the upstream basin and the highway site. And based on the imperviousness of each site, we generate these runoff coefficient statistics from for each event, and the statistics are based on data from like 70 highway sites and I think 136 non-highway sites nationwide. Now the upstream basin has runoff, but it also has the pre-storm stream flow. So that's also randomly generated based on several variables. And we've done all these statistics for you. So for the upstream basin, the upstream flow is the pre-storm flow plus the runoff, and the highway site has runoff. We add the upstream flow, the highway runoff flow, that gives us our downstream flow for each event. And from that, we can calculate those downstream storm flow statistics. SELDM supports the environmental decision-making process. So if you think of a highway as a long linear feature, in theory, if you're putting in a new highway or you have to look at a basin, a highway is unique that it could cross, hundreds of streams in theory. So if you have to develop the watershed model for all these points, you could get bogged down for years. I worked on a watershed model study where the guy was using HSPF in Rhode Island, and it was like a 4-year study, and it was like $2 million to come up with these basin-wide models to try and get point estimates. So you can invest a lot of time. In contrast, you can come up with fairly decent estimates using SELDM, once you get the feel for it in, 15 or 20 minutes. So at the first level, we're looking at the idea of hydrologic similarity. We're looking within a region for, what are statistics for the region. We're assuming they apply to our site. So we use ecoregions for pre-storm flow, precipitation, and water quality. And we can use EPA rain zones for precipitation. So you can come in not knowing much about the area or the site of interest, and you can get these regional estimates really quick. The next level is a second level analysis. If you use nearby sites in SELDM, those are also very quick estimates. You could also use statistics from nearby sites that you get from outside SELDM that might take a little longer. Again, we're assuming hydrologic similarity, that the hydrology of this nearby site is much like the hydrology of the site of interest. And in this case, with the second level analysis, we're looking at proximity. So we're saying because there's other basins nearby, it's probably very similar. And then, if there's like an endangered species or it's a very controversial site and you really need to dig in, there's this third level of analysis where you use user-defined statistics from data that you collect right there at the site of interest. There's a couple problems with that. Data collection is expensive. To get good data, you might need to monitor for 1 or more years. And even if you do all that, let's say you're putting in a new highway, the basin that you monitor before the highway is put in is not going to be the basin that exists after the highway that puts in. Usually there's more development upstream, et cetera. So this is an example of the precipitation statistics that are already in there for you. So we did statistics for 2,610 hourly precipitation data stations nationwide. The black polygons are the EPA rain zones. These colored pastel polygons are the U.S. EPA ecoregions. So for a level 1 analysis, I could just take one of the regions and get the average or median of all stations in a region. If I go to a level 2 is really easy. Let's say I'm at this place in Nevada that's kind of out in the middle here where you see these 3 little rain gauges here. If I know something about my site, I could just take the average of these 3 rain gauges, or if 1 or 2 of them were more representative of my site of interest, I might pick, those. So it's really easy to click and get the average or the median of, 1 to 100 rain gauges near my site of interest. Okay, similarly, we've done this pre-storm stream flow statistics for you. It doesn't make sense to do regional estimates based on rain zone for stream flow, but we did the ecoregion. Again, if I'm in an ecoregion, I just do the average or median of all stream gauges in an ecoregion. Or again, if I'm in Nevada here, we've got these 5 little stream gauges in the middle of Nevada. I could just pick one or a couple of them that are most representative of my site and use statistics from those. Or recently, we did statistics for the SELDM statistics for like 20,000 gauges nationwide. If you go into the USGS StreamStats application and click around looking for triangles, you will get statistics from any nearby gauge that's, I think, 3 years, that has 3 or more years of record. So those are now available nationwide. And again, that's an order of magnitude more stream gauges, from 2,700 to something like 20,000. For water quality, we did data mining from the National Water Information System. We came up with 24,581 stations and about 2 million samples. I think that was of 2004 or 2006. And not all these statistics are in SELDM because we didn't want to overwhelm you with choices, but we have another tool that helps you get the water quality data that you need. Not every constituent is available at all 24,000 stations. For sediments available at a lot of stations, once you get down to something like total copper, it's, might be available at 1,000 stations nationwide. 24,000 stations sounds like a lot, but there's like 9 million miles of stream. In some of these areas like the Northeast, looks like there's data everywhere, but the size of the dots versus the size of the states. Sometimes when you're looking for data, you need more. But again, we provide a lot of statistics for you, but we also provide the tools to, if you're looking deeper than what's available or what we've provided the tools for you to easily come up with your own numbers. So I love George Box and his quotes. He looks like somebody's grandpa, but the saying here is beware of overconfident modelers. What George said was essentially all models are wrong, but some models are useful. And remember that all models are wrong. The practical question is how wrong do they have to be not to be useful? So SELDM's a fairly simple model. It's calibrated by having the good statistics we've calculated for you, but it's not a process-based model. It's trying to capture what goes on without capturing how things go on. But you can be fooled by some of these really complex models that have hundreds of knobs and buttons that you can play with to get an answer. Sometimes with a more complex model, you can get a worse answer than with a simpler model. And because there's so much uncertainty in hydrologic data, you're often fooling yourself when you go to these ultra complex models. For example, just to give you kind of an idea of hydrologic uncertainty, there's like 20,000 stream gauges nationwide. Many of them have been run for, more than a century. When the USGS developed stream stats equations to predict like high flows, mid flows, floods, when you look at the uncertainty of these equations that are based on, multiple basin properties, a lot of these relations have a really good relation will give you an answer that's within twice the answer it gives you to half the answer. But very often these predictions for just stream flow, which is a lot simpler than storm flow and water quality all combined, very often a lot of these predictions are, the saying in hydrology is what's in order of magnitude among friends. So it can be plus or minus in order of magnitudes. SELDM, as I was just saying, SELDM's a lump parameter model. There are battery engineers who try and figure out the best way to build a battery and, what's going on within the battery at a molecular level. We don't want to do that with SELDM. What we care about is, what's the voltage over time. That's most battery owners worry about, what's the drawdown on my battery. They don't worry about the molecular components. So SELDM is this lump parameter model. We're looking for the results, what's going on, rather than why it's happening. So that would be more of a research model where you're trying to figure out why it's happening. As I mentioned, there's a lot of balance between the complexity of the model and the amount and type of data needed. So this is a graph from the EPA, and it shows uncertainty on the vertical axis and model complexity on the horizontal axis. So the green line is model framework uncertainty. So if you have, in theory, if you have a more complex model, it's going to represent what's happening better. The problem is, as you get more model framework, if you reduce the framework uncertainty by getting a more complex model, your data uncertainty goes way up. And so what we tried to aim for in SELDM is kind of to try and get at that point of minimum uncertainty, so that by calculating the statistics for you and having a simpler model that we'd be able to give you good, robust answers without having to, do a ton of work to get them in for you. All right, right now I'll do a quick case study. This is Howard Brook, a 1.34 square mile basin in Northborough, Massachusetts. So this is near my office. The highway along the bottom of this graphic is I-290 in Massachusetts. That's outlined in the blue area. I think that's about 6 acres. The black line is the stream stats delineation for this basin. The red line is the stream going up to the basin divide, and the drainage area for this basin is the pink area. So we used the local hydrology to generate 1,648 storms over a 29-year period. This graph shows the total phosphorus concentrations. We use some local mass highway data to calculate statistics. So from that, we calculate these gray dots are the highway runoff values. So we can use that to look at the risk of exceeding water quality standards, for example. So we have total phosphorus concentrations on a log scale on the vertical axis, and this weird scale is a probability scale on the horizontal axis, and that stretches out the risks at the tail ends. Because, what do we care about? We We care about floods and droughts, and we care about the highest concentrations, usually the highest loads out at the end. Those that have a remote chance of happening but have a bad effect. So when we're looking at total phosphorus, we can see this red line is the 0.5 milligram per liter standard used for most water quality discharges nationwide. We can see that with the gray dots with the highway runoff, we have about a 2% chance of exceedance. And EPA nationwide, they tend to go with a 1 in 3 year exceedance. So in this area of the country, that's about a 0.5% exceedance. So we can see that we'd have a risk of exceeding this standard nationwide. We also get decision-making information because some regulatory folk want to use the in-stream standard, the 0.1 milligram per liter, to apply it to discharges. So with the highway runoff here, we see that 50% of those highway runoff discharges are going to exceed that. So there's no way we're going to, meet that standard. And this value down here, the white line at 0.02375 milligrams per liter, that's what EPA is now looking at for ecoregion 59. That's the northeastern coastal zone. So if they applied that as a discharge standard, we could see that the highway runoff would exceed that about 95% of the time. So there's no way we're going to meet it. Now the yellow triangles are the grassy swales discharge concentrations. So this would be when we run SELDM, we can see what our risks are with or without a BMP. So this is a grassy swale. We can see that with the grassy swale, we might be able to, we don't quite get down to that 0.5 1 in 3 year event. So we might still exceed that water quality standard, but very rarely. And again, when we get to this 0.1 standard, we can see even with a grassy swale, we can't meet that, and we really can't meet that new EPA recommended standard for the receiving waters. So this is kind of the risk-based information that SELDM can provide. So SELDM also generates background water quality. So we have here again is total phosphorus concentrations on a log scale and that probability scale. So the yellow graphs are, or the yellow symbols are local data from a local watershed, and the blue data, or the blue symbols, are the regional ecoregion level 1 estimate for water quality. So we can see in this case for total phosphorus, our regional value is right in among some of the values we'd end up with if we use local data. And we can see with that 0.1 criteria, these upstream concentrations are all going to exceed that 0.1 criteria more than that 0.5% of the time, that 1 in 3 year. We're going to be kind of way over that in terms of risk. The Northeast Massachusetts has fairly high natural phosphorus concentrations in the soil. So what we see here is the results of that maybe the base flow concentrations can meet these receiving water standards, but storm flows cannot, even in relatively pristine basins. And I guess to put that into perspective, we can see these, the triangles, the upward facing triangles, the lowest concentrations, that's the outlet of the Cambridge Reservoir. So that's a drinking water reservoir with a 6-month holding time. So imagine if you could build a BMP pond with a 6-month holding time. So even with this huge drinking water reservoir, during storm events, water quality will exceed these criteria more than would be allowable with the 1 in 3 year standard. So again, this is the kind of risk-based information that SELDM can provide. So this is the third graph. Again, it's total phosphorus on the vertical scale, and then the horizontal scale is the risk axis. And what we see here is upstream, downstream, and the highway runoff. And we can see in this case, even though Howard Brook is only 1.34 square miles and the highway is 6 acres, kind of a relatively large ratio, we can see that the highway really doesn't have an effect on water quality at this site. And I think by and large, that is because, the highway doesn't have an effect with or without the grassy swale, and You know, by and large, that's because the background water quality is fairly high in this area of New England. And you can see the highway runoff, which is the gray circles here, isn't vastly different from background water quality. All right, that would be a river basin example. SELDM also has an annual mass balance model for lake analysis. So I won't get into the details of this diagram, but basically with the lake analysis, you have the rest of the basin is contributing 365 days a year, you know, if it's a perennial stream, 24 hours a day. The highway is the second part that contributes while runoff is occurring. You get the loads from the non-highway area and the highway area of the basin, and it will calculate long-term average annual concentration. So it's basically, if you know about lake analysis, it's called the Vollenweider model. And for annual loads or for like TMDLs or lake analysis, your highway site can be hypothetical. So this is the Situate Reservoir in Rhode Island. The yellow lines are the state highways or state roadways in the area. If you're doing annual analyses, you don't really need to worry about the timing of the hydrographs, so you can use some dummy variables for the highway hydraulics. In this case, if I was looking at chloride into this basin, I might want to use this whole area of highways. If I was looking at something that was bound up by the soil like total phosphorus, I might take a subset of these where the highways directly drain into the tributaries of the reservoir. So this is where some professional judgment can be used. So this shows you the population of annual loads for that Massachusetts water quality. And this is with and without BMPs. You could do it for an actual site, or again, you could come up with a yield per acre. In this case, it's total phosphorus loads in pounds per acre per year. If you're looking at a TMDL, you want the long-term average, because the average is the sum of the total load over the whole period, in this case 29 years, divided by the number of years. So we can see in this case that the highway runoff varies, and when you run SELDM, you also get this risk-based information when people talk about the margin of safety or looking at uncertainty in TMDLs. We can see in this case our annual loads range from half a pound per year to like 1.375 pounds per year. Then on average, it was about a pound per year per acre for the highway. Grassy swale wasn't great at reducing phosphorus concentrations, but it has a fair amount of infiltration. So between the infiltration and the reductions that do occur, the reductions that occur in a grassy swale tend to be the worst concentrations get reduced. Some of the low concentrations don't get reduced. But we can see that even with just a grassy swale, we can get substantial reductions in annual loads over a long period of time. So I guess learning outcomes from this is, as we saw in the last talk, SELDM has been thoroughly vetted. We developed it in cooperation with the Federal Highway Administration with a lot of input from EPA. We wanted regulators to accept it. We had a bunch of state DOTs play with the model, give us feedback, what they could use, usability, looking for errors. So we wanted to make sure we provide a tool that will give people answers they need and that it's, usable. We didn't want to come up with another very complex model that you'd have to be an expert modeler to use. Again, as I showed with some of these risk graphs, it's designed to assess the risk to help decision making. If you're in NEPA, you run SELDM, it shows that you have very little risk of having any changes in the downstream water quality. You could say this is a FONSI, right? Finding of no significant impact. If there are more risks, you might try more advanced BMPs to see if that would solve the problem. But again, you can get this risk-based information. It supports varying levels of input. If you're looking at a linear highway and you have a whole bunch of stream crossings, you could do these region 1 analyses, level 1 regional analyses to quickly rule out the things where the highway may not make a difference, and you can focus on the crossings that potentially are a problem. It's a lump parameter planning level model. it's calibrated by what the statistics you put in. People have asked us, can you compare it to available data? When you go out and look, I have not found a comprehensive study where they're looking at highway runoff, they're looking at upstream and downstream. But SELDM is not designed to like history match. It gives you risk. It doesn't give you like what actually happened over the last 30 years. Again, it's pre-calibrated because we've calculated all these statistics from massive data sets of tens to thousands of sites, hundreds of storms, thousands of concentrations. So it's robust and pre-calibrated. We've done the work for you. And again, SELDM is more robust than the required inputs would suggest because the development project assembled and synthesized these large data sets. And once you get used to playing with SELDM a little bit, it's really easy to get some answers within an hour.